Lab 4 oscillations. The purpose of this lab is to understand and predict the motion of an oscillating spring mass system. To do this, we'll be looking at the momentum principle and the energy principle, and a brief preview is that the computer model pretty closely matched experimental data, which shows that seemingly complicated motion can be modeled using the same fundamental principles, and that for a system where there is no external work, such as a spring mass system in the Earth, the change in total energy was zero. So the first equation used was the energy principle, which says change in energy is the work from the surroundings plus heat transferred from the surroundings to the system, or vice versa. And then Newton's second law of momentum principle is used to model the motion by considering all the forces that are shown below. And then there's also some equations describing the energy. So the reason that we're using this is because we're close to the surface of the Earth, so that's why we're using Fg equals mg, and gravitational energy is mgh. And we're using the momentum principle to predict the motion and the energy principle to predict the energy changes in our experiment and data. So our main assumptions are that force of gravity is constant, that's why we're staying close to the surface of the Earth, and that these are all the forces that are acting on the system, so there's no friction essentially. For the experiment, the system is a spring mass and the Earth, and the surroundings is the air. So these are all the initial conditions for the constants, and essentially what we did is we took the video of the recording, which slightly stretched and released a vertical spring mass system that kind of also moved horizontally, and then using tracker that moved horizontally like a pendulum, and then using tracker to analyze and plot the coordinates of the mass against time, and finally exported that data to CSV file to compare against the computer model. So this is what that looked like. As you can see, there is oscillation in the x direction and also oscillation in the y direction. So we took all this data and turned that into a CSV file. So for the code, we copied the exact same conditions from experimental data. The only difference is that the initial velocity was calculated using the data points. And then afterward, use the momentum principle and the force equations to model the motion. So that's what this whole first half here is, right? Calculating the net force and then updating the position and velocity. And for the second half, use the energy principle to model the changes in energy. So that's what that looks like here. It's just applying all of the formula, such as kinetic energy is half mv squared, and spring energy is half ks squared. So this is what the results from the code look like. This is essentially just showing the trajectory of the model compared to the experimental data in the red. It's not shown here, but they were very, very similar, but the red slightly lagged behind. And this just shows the change in energy. One important thing to note is that the change in total energy was zero all the time. So as you can see, the data was very similar for the model and the prediction. However, there is a slight delay or slight difference in both that I believe was mostly accounted for due to frictional forces. So this is what's written here. The computer model mass moved slightly faster in experimental data, and that gap increased. I think this is because that friction was not considered. So air resistance that slowed down the mass caused that difference between the position. And there could have also been some inaccuracy in the physical constants, such as the spring constant or the spring at rest, that weren't accounted for. So one key thing to note is the energy principle was satisfied because the net energy was unchanged. That is, the delta E was always zero. That's because there was no work from the surroundings because the system was the Earth and the spring. So the work from the surroundings was zero, and then we assumed that everything was the same temperature, so the heat transfer was also zero, so therefore the change in energy was zero. And then secondly, the period of the oscillation. Now, it's around 1.6 seconds in the x direction and 1.5 seconds in the y direction. That's looking at the red peaks. It's just a coincidence that they're similar since they actually measure different periods. The horizontal one is kind of like the pendulum motion. Meanwhile, the vertical one is the actual period of the spring oscillation itself. It's not exactly it, but it's pretty much how you could think of it. So in conclusion, the computer model closely matched experimental data, except for a slight delay due to the frictional forces, and that seemingly complicated motion can still be modeled using the same fundamental principles, showing that this physics, it always still applies regardless of the complexity of the system. That is, the energy principle is always satisfied since the change in total energy was zero. Thank you.